So we've made these things, we've looked at their 3D structure, but there is a problem, right? When we start to build these molecules together, we've noticed that our geometries are things like 109-degree angle, or 67-degree angle, or things that are not orthogonal. If you think about those atomic orbitals were all in 90 degrees to each other. So we've got to come up with a way to reconcile that. But first, we need to describe so we're going to talk about two different theories of bonding. The first is going to be valence bond theory, which is going to account for some of that, and then we'll look at a more advanced model, which is called molecular orbital theory. Valence bond theory talks about electrons as being an overlapping of atomic orbitals in a bond, so that's pretty easy to understand. Well, I've got my hydrogen's s orbital and my other hydrogen's s orbital, and they're sharing an electron, and their two orbitals are overlapping. Right? The orbitals are maybe hybridized, but they're still essentially going to belong to one atom. The other model we'll look at is called molecular orbital theory, where the orbitals are going to combine to form new orbitals, which are spread out over the entire molecule. So electrons are in orbitals which belong to the molecule as a whole. Valence bond theory is a quantum mechanical model which shows how electron pairs are shared in a covalent bond. Covalent bonds are going to be formed by the overlap of atomic orbitals, each of which contains one electron of opposite spins. Remember, we had these electron spins happening before. One was spin up, one was spin down. Now they're going to share an overlap, and one will still be spin up and one will still be spin down. Each of the bonded atoms maintains its own atomic orbitals, but the electron pair in the overlapping orbitals is going to be shared by both atoms. The greater the amount of overlap, the stronger the bond. So we can combine this, and it's going to be what we call a sigma bond, by overlapping these orbitals directly. It could be from two s orbitals sharing an electron. It could be from two p's. It could be from an s and a p. It could be some d's that are involved in there. So as long as it's this direct end-to-end overlap, that's what's going to make it a sigma bond. So our electrons are going to occupy atomic orbitals. So here is a hydrogen with one s electron, and here's another hydrogen with one s electron, and they combine and they're going to overlap and they're going to share the electrons in both their orbitals. Covalent bonding results from the overlap of orbitals. Right? We could do this with p orbitals. So here's fluorine, right? So fluorine has some filled orbitals, right? So we got two electrons in here and two electrons in here. Those are our p's. And then we've got this px on one fluorine and a px on the other, and it's only got one electron in each orbital. They're going to overlap, and now it looks like, from the fluorine's point of view, that they are sharing that electron and that orbital is filled. If we have a molecule like hydrogen fluoride, right, the hydrogen's got a half-filled s, and our fluorine is missing in one of its p orbitals an electron to complete its octet, and they're going to overlap and they're going to share. And so let's take a look at beryllium chloride. Our Lewis structure for beryllium chloride is going to have beryllium as the central atom with two chlorines singly bonded on either side. The Vesper model predicts that this is going to be linear with both bonds that are equivalent. But if we look at the electronic structure of beryllium, right, we've got a 2s2 configuration with no unpaired electrons. So what we do is we can give this beryllium, we can put it into an excited state. That's what this little star means. It's got a little bit of extra energy. So we give our beryllium a little bit of extra energy. We promote one of these 2s2 electrons into a 2p. Now I've got an unpaired electron in p. This orbital is free to share that electron with the chlorine and do an end-to-end overlap. And this s orbital, it has one electron in it. It's free to do an overlap end-to-end with this chlorine over here. Okay? So what we've got is something that is a process called hybridization that is going to explain this process. It refers to the mixing of native atomic orbitals to form special orbitals that are used in bonding. Atoms can adopt different sets of atomic orbitals or hybrid orbitals from those in the free state. So our regular old atoms, those are our s, p, d, f orbitals. We can use those in bonding, but sometimes they're not just going to be what we need. We're going to need something a little bit different. And so we'll invoke this idea of hybridized orbitals. Now keep in mind, hybridized orbitals is different from resonance. Resonance is when we've got two different Lewis structures and they form an intermediate structure that is sometimes called a resonance hybrid. Here we're talking about hybridizing or mixing two orbitals, two atomic orbitals together. And it's going to be a little bit different than they are than just the regular atomic orbitals. So let's take a look at the bonding in methane. So we've got carbon, 4 hydrogens are attached to it. If I look at my electronic structure for carbon, right, I've got space to do 1, 2, 3, 4. I got 4 empty spaces here, but I only have 2 unpaired electrons in our ground state configuration for carbon. So what we're going to do is we're going to combine some of our s orbitals and some of our p orbitals together. Right? And now we've got some 4 valence electrons and 4 unpaired electrons. So we've kind of combined these guys and we've kind of promoted them. Right? We're going to move some electrons up there. So now we've got 4 unpaired electrons. But that's not the whole story, right? Because in our molecule, CH4, right, this would result in 4 non-equivalent orbitals. And we know that the bond between each of these hydrogens is exactly the same. Right, so these 3 are going to be the same. They'll be degenerate. Remember, that's our word for the same energy, degenerate. But this one's got a different energy level. So the hydrogen that would try to form a sigma bond here would not be the same strength as a hydrogen forming a sigma bond over here. So how do we reconcile that? Well, we're going to take these 1, 2, 3, 4 orbitals, and we will hybridize them to make 4 equivalent orbitals. And we're going to call these guys hybrid orbitals. The overall energy of these orbitals is a little bit less than the p, and it's a little bit more than the s. Right, so we're going to take 3 p's and 1 s, and we're going to combine them to make 4 new orbitals, and we will call them sp3 orbitals. So I've got an sp3 orbital, an sp3 orbital, sp3 orbital, and an sp3 orbital. The number of hybrid orbitals that you make is going to be equal to the number of regular old atomic orbitals that you start with. And we'll talk about the naming in just a second. Right? So our atomic orbitals on an atom are going to mix to form hybrid orbitals. And our orbital shapes, our boundary surfaces, are pictorial representations of the wave functions. Right? Remember, our wave functions are just mathematical functions that describe the position and the momentum of an electron, and the square of that is going to give us our probability density. But remember that mathematical functions can be combined, right? So if you consider the simultaneous equations, 2x plus 3y is equal to 12, and x minus y is equal to minus 1, we can solve for both x and y. Right? You can add or subtract equations. Right? So if I've got an equation like 3x plus 2y is equal to 13 and x plus 4y is equal to 11, we can solve for x and y. Right? And we're going to do something similar here with our atomic orbitals. We're just taking those 2 wave functions, we're running them through the math, and we're going to end up with these hybrid orbitals that are going to have a unique shape based on which orbitals we combine. All right, so let's take a look at our first one. We're going to take an s orbital and a p orbital. Notice that the hybrid orbitals are going to kind of look like they've got character for both of them. Right, so it's kind of a little bit more spherical than the p orbital, and it's got the directionality of that p orbital where the s is just a sphere, and it's going to maintain that direction on that. And this one looks like it's on the x-axis. Right? So we're going to end up with combining 2 atomic orbitals, and we're going to get 2 hybrid orbitals, right? So we've got 2 atomic orbitals, and that's going to give us 2 hybrid, right? And these guys, notice, are called sp because we've taken one s and one p. We can take the two sp orbitals are going to point in opposite directions to one another. So the x component of that p orbital is going to give it that directionality. So we'll take the s, which is in yellow, and then the p, which is in blue, and we're going to combine them into sp orbitals. We still have these leftover p orbitals with nothing in them. That's why these are kind of drawn as empty balloons. And then we've got some directionality. And there's a little bit of a lobe coming out of this guy for this one, and then the same thing for this guy on the other side. They're just not drawing those little lobes in there as well. Once we've got these orbitals, our hybrid orbitals, they can do end-to-end overlap too, just like an s or a p or a d orbital. So our s and p orbital overlaps are going to happen here with our beryllium. So now this guy, it can interface with this half-filled orbital on chlorine, so the chlorine's p orbital and then the sp orbital from the beryllium are able to overlap. That's what we're seeing here. They form this bond. I'll call that a sigma bond. And over here, our other sp orbital is able to interact with the p orbital from this chlorine. They're going to overlap and form a sigma bond over here. Let's look at another example. So, for example, we've got boron trifluoride, BF3. If you draw a Lewis structure for this, for BF3, right, it's a boron with 3 fluorines around it. Our VSEPR shape says that it's going to be trigonal planar, and all these bonds are going to be equivalent. But if we look at boron's electronic structure, we've only got one unpaired electron. We can make an excited state boron and give us an s orbital and then 2 p's. Right, so if we look at that, we've got this s orbital, which is spherical, and then we've got a p orbital in one direction and a p orbital in the other way. But look at the direction that these p's are in, right? These are orthogonal. They're at 90-degree angles to each other, right? And this guy's at 90-degree angles to this one. And we know that this shape in here is sure not 90 degrees, right? It is not 90 degrees. So our atomic orbitals, right? We can't just do this, right? It's going to give us the wrong shape. So we have to use this hybridization model where we're going to take one of our s's and 2 of our p's. Notice that this guy's got some x component to it, and this guy's got some y component to it. And we're going to end up with 3 sp2 hybrid orbitals. Right? So the number of orbitals that you start with, right, I've got 3 atomic orbitals, and I'm going to end up with 3 hybrid orbitals. Right? And these guys are called sp2 because we've used 2 p's. And you'll notice that these hybrid orbitals here are going to, and they don't look like this. It's just the same thing repeated 3 times. They've got this lobe structure. Here's one of them, right, because we've got this vertical component. And then it kind of goes the other way where we've got a little bit of x component going for this guy, and then we've got a little bit of x component going for this guy. And the angles that come out of this are going to be exactly the angles that we need to give us that trigonal planar structure that we know that our boron trifluoride is going to adopt from VSEPR. Right? So we're going to take our 1, 2, 3 orbitals over here. I got 3 orbitals on the left. We're going to make 3 orbitals on the right. When I combine them, I'm going to do away with those 3 and make 3 new ones. Right, one's pointing on y, one's pointing on both x and z, and one's pointing on x and z in the other direction. Right? And then I can combine those with our half-filled orbital, p orbital from fluorine. Right? So our fluorine over here is missing one, and so I can do an end-to-end overlap between our sp2, this sp2, and I can do an end-to-end overlap with this sp2. And an end-to-end overlap with this sp2 into these fluorine's p orbitals, right, which is missing 1 electron. So we've got this overlap here, and that is our sigma bond. And we got an overlap here, end-to-end, that's a sigma bond. And this overlap here, that's a sigma bond. So our shape, our geometry in 3 dimensions comes out of the math that happens when we do the linear combination of these atomic orbitals to get our new hybrid orbitals. Right, let's take a look at methane. Right? So our Lewis structure here for methane kind of looks like a plus shape. Right? Vesper shape predicts that we're going to have tetrahedral with all bonds being equivalent. Right? If we look at our carbon, it's only got 2 electrons to work with. We can say, all right, well, let's try to promote one of these electrons from our s orbital into our p orbital. But when we do that, right, we don't have the right geometry because this is going to be in one's going to be in x, one's going to be in y, and one's going to be in the z plane. And our s orbital can overlap with anything because it's a sphere. It doesn't matter what orientation you put it in, but these are definitely going to have orientation. But none of those orientations are going to be in this trigonal or this tetrahedral position, right? Maybe this p or maybe that py orbital would, right? But then what do you do with these guys on the side, right? They're not going to be orthogonal at all. So we can't have this overlap with 90-degree p orbitals to give us this structure. And we know that this over here, right, is not the same. It's not going to be equivalent energy to these guys, right? So we need this hybridization. Right? So when we do that, we're going to generate a molecule that's going to have 4 sp3 hybrids. And notice this carbon has 4 bonds to it. Right? How many bonds does carbon kind of want to have, right? It kind of want to has 4 bonds, right? And so you see a lot of sp3 hybrids in carbon. Those tetrahedral structures, those are coming from things that are going to be sp3 hybridized.